group 9, and we are going to talk about in this video of the milestone 1, the first degree. First, we have the call graph. We make this to analyze the function, how this works, the code, how the functions are called, and it all start with the puzzle div find cpp. That in the main function they have two functions, but the main function calls everybody else. And with the main function first called the puzzle init context with a puzzle context variable, and this class is localized in the program puzzle.c. After this is called the function puzzle div.cpp, that is where is the main function, but in this case it goes to the function parse ops. The parse ops manage the function that it will be using when he's reading the inputs of the terminal. Each function this puzzle div have called several times to the tunables class that contain the different functions of set constant barrier for cropping, set max cropping radio, set auto crop, set max height, set lambdas, set noise cutoff, set p ratio, set max width, and the calls to the different class that is in the PGA TOPT CPP to compare the variables. In all these functions of the tunables, there are options that could be made for the image. After this, it calls to in the main, it calls the init CVS to initialize that CVS, and it's in the program CVS C. In the CVS-C, it also calls to the function fill CVS from file to localize the file, and this calls to different functions, how we can see it here. It calls to the dbsc from file. We cannot access to the dbsc file. We don't access to the dbsc file from the main. We access directly from the CVS. And with the dbs file, we call to the file dbs from file with puzzle context and puzzle dbsc, and we access to the pclinit view and the init labs. And with this, we process the image, and if there is an error, we call to the program puzzle C that contains the class puzzle error bug. And also, the CVS calls to the pclinit dbc to initialize the variable, and to the free dbc to make it free, the variable. After the puzzle also calls to the vector normalized distance. This function calls to the vector sub and the vector Euclidean length, so we can obtain the length that is from one image to the other and see the difference that there is. This is the mathematical process that it will make the program. The other two functions that calls the main is the puzzle free CBSC, like the one of DBSC, but in this case for the CBSC, and for the free context to deliver the free context. And we have also to say that the vector ops and for vector sub and vector Euclidean length equals to the puzzle bug in case there is a mistake, so it will be localized here.
Okay, so we see from this call graph that actually we will involve many functions, and we are going to explain the data dependency. So we already implement our own version of puzzle div, which is used to compare the distance of a reference file to a given directory. That means it will search all the nearest files or almost equal files. The first 10 of them will be listed. Okay, let's see the code. Here, now you can see that on the left-hand side, it is our main program. Generally, the idea is to compare each of the files in the directory to the given reference. And we computed the distance one by one, and then we sort it. So this is a standard part. But we will look about on the library puzzle, because once we see that here we can see that the puzzle involved the initialization C vector. After the initialization, we see that there is a puzzle field C vector from file. So this is actually one of the greatest among the consumption or the runtime hotspots in the code that we can actually see from a diagram which we will show here. Actually, in here we find that a few function code will be involved here. So we are going to explain and we to see the code to see what's happened on the data dependency here. Now, first we look at the library puzzle, the source file, the dvet or the cvet first. And from the field cvet from file, we actually see that it will call the function field dvet from file, which is located in the source dvet.c. So let's see. Here we can see the field dvet from file. Let's scroll it down. Here we can find that actually it involves plenty of calls, and we can analyze it. Actually, we find a few of them that will be called for the using the ON square looping. So let's do it one by one. Okay, first of all, we will discuss about the auto clock field here. Now let's roll on the auto clock field, which is called for many times, and especially when we do the hotspot analysis and we actually find the auto clock access and auto clock field consume of the most of the running time. Now, in the auto clock field and similar code, we analyzed it that we can find a similar structure here. We can find the two-dimensional looping here, and which is actually just used to sum up or to put the corresponding values from the field to the map pointer array. That means it's just get the values from an array to write it to another array. So probably we can do it in the parallelization, and we can just do the computation of the indexes. So this is one first part that we can do the possible analysis, the parallelization. It is line 199 to line 204. So the next part that we can performing the parallelization would then be, let's see here. Well, for the auto clock access here, we again find a similar structure, a ON square looping that is used to do a sum of a particular values. And here, we suspected that it is possible to do the parallelization, though there may be a race condition, but it can be solved by the Select Reducer library. So probably we are going to work on this if it is necessary. But clearly, we can see that the chunk contrast will be used if we try to do a naive parallelization, say doing a select for, then this variable will be accessed simultaneously, and therefore there will be a race condition. Now we are going to discuss about the next possible path that calls up the most time. The next part that we suspected of a high consuming time would then be the puzzle gets AVG LVL. Again, we see the ON square structure here, and here it is again doing a sum of from a given array or two-dimensional array. So if we can solve the race conditional issue, say by mapping all the AYs plus plus AAs plus plus to the corresponding indices and use the Select Reducer operation add or operation sum, then we may possibly parallelize this part and save a bit of the ON square here. Now, for a similar structure, then we actually can find in very similar in a similar code it's puzzle solved GEDLVL. So we can scroll to here and find it. It is located at 294 the number line 294 and up to number line it is 310. Here, a large two-dimensional looping. Here we suspect again the LVL counter can be done in a similar way, but if we cannot solve the race conditional issue, then there must be a dependency between each loop because it is definitely a loop carry dependency. But we actually found some other possible stuff that we might do on it. So let's see. The next one is the puzzle add neighbors. Again, we see that there is a ON square looping, which involve another cumulative computing or storing the values from AVG, LVLS. So this can be done in a parallelization, actually without any data dependency. If we can just compute the neighbor, the indices, and this part with a pre-computation like the AX times the number of columns and added the AY, then actually this can be done in the parallelization by using 204. Probably there will be no data dependency if we do it like this way. So the first part that we may work on would then be this, the puzzle add neighbors. And of course, we find other similar structures in cvet.c and vetop.c. They will be explained in a very similar fashion. So basically, our parallelization strategy will be trying to hoping to find a way to do the parallelization on those ON square looping, and if possible, whenever there's a sum computation, say a total sum of the n square involving in the web ops, like computing the Euclidean length, then we try to use the Silk reducer so that we can speed up when there are a number of plenty of available resources. And this actually helps us to compute the distance between a given image and the reference file in a very simultaneous manner, so that whenever the size is computed, just it is the span would just be like just doing the largest work between a reference file to the largest image. So with this manner, we believe that the scalability is actually depends on the number of available cores, and it can be done as good as possible if infinitely many cores is provided.
In cvec.c, there are two regions which can be parallelized with Silk. The first is from line 76 to 93. Here we can change this do-while loop with a Silk for loop and parallelize the way the counters increase. This transformation causes race condition problems in counters, but this can be avoided with proper checks. The other region is in lines 103 to 113. Also here we can use a Silk for loop to parallelize this part. This parallelization doesn't cause any race condition problem. File vector ops.c, there are two parts of codes that can be parallelized. The first one is in line 28 until line 48. Here these two do-while loops, we can transform them in Silk for loops and parallelize the code. The second part is in line 64 until line 72. Again, it's a do-while for loop. Also with the Silk for loop we can parallelize this, but maybe we cause some race condition problems because of this variable, this counter t. Again, with proper checks we can avoid these problems.
In the main program, we are going to parallelize the for loop because we only need the in the main program we are going to parallelize the for loop because we already have the C vector of the first file. So we are going to calculate the C vector of all the other files and computate the distance. We can do that parallelly because each file is independent, so we can calculate the distance of each file at the same time. Another part that we can parallelize are the sorts. We can do it parallelly and after wait here for everything and to print it on the screen.
Okay. Now we are going to analyze the profiling details and to see what we can conclude from this profiling. So first of all, the picture shown here is the large.png that displayed the time that we used our own puzzle differ program to check the games with a large reference file and the whole set of the provided image files. It actually spent 17.2 seconds, and we come up that puzzle auto clock runs in 3.5 seconds, and similarly we can see here. And on the other hand, we also compare with the small picture here. We can see a small picture here. So let me do it a better way. At the small picture here, we can actually see that we only spent 15.6 seconds. But when we look carefully, it gives us some hints on how we do the optimization or the parallelization here. Now, first of all, when we see the puzzle auto crop access, it's dropped from 3.5 seconds to 3.1 seconds. That means the size actually determine the running time of this auto clock very importantly, and it may have a strong effect on when we try to scale on a very large picture or huge amount set of the pictures. But on the other hand, we also observed that the second function called GD image get true color pixel actually do behave in the same almost the same seconds. So we think that this cannot be optimized or parallelized anymore. And indeed it is from the library GD and we can do nothing on that. Now we look at the third one, the P puzzle get view from GD image. It is what we aimed to parallelize as well, because we see that when we try to do a small file and a large file, there's already 0.4 seconds. Now for the other parts, we can also see 2.2 seconds and similarly. So we are going to see all the functions or all the codes or the lines that we can optimize from the profiling. Now here you can see the picture which is labeled the bottom up. The bottom up sorted by the longest CPU time that the code that will cluster into. Then we see that as we saw it before, auto clock access and auto clock field, and therefore we'll look into this to see which code actually gives us the most running time. So the first is the auto clock. Here we can analyze the CPU time and actually we find the chunk contrast here, which consists of almost the adding part here is almost 2 seconds per images. per set for the whole set of images. But then we actually know that we can speed up this if we use the Cyric reducer. And the data dependency is of course a loop carry dependency if we just use a naive Cyric for to do here. Therefore, we need the reducer library. And for the most part of them, I think we can optimize this or parallelize this from ON square to the number of available cores. Okay, then for the next part, we are going to show that is the code that will be run for the most time. So this is from the dweb hotspot here. Now we can also see that the first week here is involved with some, and most of them are just located inside the two-dimensional looping that we mentioned it previously when we analyzed the source code. So for each of them, I will show the pictures and we will see what we can do more and the exact time that is spent. So for the autocop reel, we see that, and we discussed it, this can be done parallelized, and therefore it's run in 1 second. If it can be done parallelly, then actually it can be reduced by very good factors, from ON square to linear time or even to constant time if the number of available resources, the number of cores are infinitely. Next, it is the soft get here and the get AVGL. These tools are also consuming very large parts of running time, and indeed we can see it's just used to do a summation of the values, and therefore we predicted it can be parallelized. And of course the get AVGL, this function, of course, it is much faster, but still it is using the summation idea. So whenever there's a summation manner part, we can try to do this, and therefore to reduce the quadratic time to a linear or even better one. So finally, it is the get view from GD image. And very unfortunately, we can do nothing on line number 256. It is a library call. But here we can observe that what it will do on the following few lines. It just take the pixel and to compute the RGB values and multiply it by the corresponding weight, and then we push into the map array here. From 250, we know that it is a pointer to an array structure or mapping structure. So if we can compute or recompute the indices y and x here, then the pixel will not be a loop carry dependency anymore. But in this way, the code written is definitely is a loop carry dependency because the previous pixel is not the same as the next pixel, and we have to wait for the whole loop to finish before we can do the next loop. But of course, there's the same for the MAPTR variables. But this is explained that we can just do by doing the x times the number of rows, and then we add the y, the traditional two-dimensional computation techniques. Then actually we can do the parallelization so that all the computation is done at the same time in the ideal cases. And similarly for this part, we try to do this, even though there's no any running time in this testing, but we guess that when we do the parallelization, this can also be done. So that's some of the profiling that we can see and the data dependency that arises in the code. For the other part, and then it remains is the puzzle differ or the find similar pictures, the main source code. Then that will be done or analyzed in the other part, and we will hope to see any further improvement if this so.